Okay, this is the makeup lecture for Monday, February 9, since we had a school closing due to the icy conditions. This lecture is about some of the chemistry of alkynes that we need to talk about. And let's go. So, remember that most of the chemistry of alkynes is very similar to the chemistry of alkenes. And that would include the addition of water across a triple bond, which is very similar to the addition of water across an alkene double bond, with a bit of a twist because that there is the extra pi system. So let's take a look at that. Now there are two main reactions that you need to recall from the chemistry of alkenes. One of those is the oxymercuration reaction. Now remember, the problem is that water itself is not acidic enough to interrupt the pi system, and so you need a catalyst. And in the case of oxymercuration, the catalyst is mercury. Handwriting is not so easy on this, but anyway, it uses a mercury salt, Hg2+, and a little bit of acid, and the acid is often sulfuric. Now, the catalyst breaks up the pi system and allows water to add. The key about the oxymercuration is that it adds in the typical Markovnikov fashion. Remember, what that means is that the incoming proton will go to the carbon that already has more hydrogens, in this case carbon number 1, and the OH, the hydroxy group, will go to the other carbon. And so the product of the first step is a vinyl, what looks like a vinyl alcohol. That's actually referred to as an enol. And the enol means that you have a functional group which is both a double bond and an OH attached to the same carbon. Now that's an interesting product. The thing about it is that because it is an enol, it is more stable actually in a different form. And so the product quickly rearranges to give a ketone as the final product. So again, this is referred to as an enol. What's made over here as the product is a ketone. And this is actually a rapid equilibrium. Now, if you look at the enol and the ketone, I'd hope you'd realize that they are constitutional isomers. And they are in a rapid equilibrium with each other. And that's kind of a new thing, right? Constitutional isomers to this point have been fixed compounds. They don't rapidly undergo an equilibrium with each other, but the keto and the enol do. And so this is referred to as tautomerism. Or, since I ran out of space, they are tautomers. And tautomers are just isomers, constitutional isomers specifically, that are in rapid equilibrium with each other. So that's one reaction to remember from the alkene chapter and apply to alkynes. The other reaction you need to remember is hydroboration. That, recall, is a two-step process. And so step number 1 involves the addition of borane. Whoops. Kind of slipped there. Step number 1 involves the addition of borane. Step number 2 is the addition of peroxide. And so when the borane adds across the triple bond, it leads to this as a product. Remember that borane is an anti-Markovnikov reaction. And so the boron ends up bonded to carbon number 1, and the incoming hydrogen, because it's actually a hydride going in, ends up bonded to carbon number 2. And there the compound waits for the second step, which is the addition of peroxide. That simply removes the boron and puts on an hydroxy group. And there again we see that this is also an enol. And as we just saw in the previous reaction, enols undergo a rapid equilibrium to the keto form. In this case, that's an aldehyde. Notice that for the equilibrium arrow, the one arrow is definitely longer than the other, and that indicates the relative proportion of the two compounds that are in equilibrium with each other. It's always more of the ketone or aldehyde depending on the particular reaction. And so, to summarize these two reactions, let's look at them side by side. Here you see a terminal alkyne reacting on the top with borane. Now it's a particular borane. Notice that the boron has only one hydrogen associated with it and two alkyl groups already on it. So that's not exactly BH3, but it undergoes the same kind of reactivity in the presence of an alkyne, or an alkene for that matter. And remember that in the case of a terminal alkyne, reaction with borane followed by peroxide always leads to an aldehyde. The other reaction, oxymercuration, in the case of a terminal alkyne, will always lead to a ketone. And so depending on the product you would desire, you would use the appropriate reagent. Now, another set of reactions from alkene chapter that apply directly to alkynes is that of reduction. You can add hydrogen directly across the triple bond. Because there are two pi bonds to deal with in the case of an alkyne, the reaction is a little bit different from what we saw in the case of alkenes. The actual difference is that you have choices of products. How far do you want to reduce the alkyne? Since there are two pi systems, do you reduce both of them or just one of them? And so you see the three options here. Option number one is reduction all the way to the alkane. So that means that both pi systems of the alkyne have had a molecule of hydrogen added across them, and so we have reduced the compound from a triple bond all the way to a single bond. Option number two, you notice says reduction to transalkenes. So if the molecule of hydrogen is adding across the triple bond, now it's only adding to one of the pi bonds, leaving the other one still present. So the triple bond is going to a double bond. And if that's happening, realize, of course, that there would be two options. And that would be, is the alkene a cis or a transalkene? And that's the third option, the cisalkene. So they are the three options. Are you taking the alkyne all the way down to the alkane? Or are you stopping at an alkene? And if so, is it the cis or is it the transalkene? As far as the specific reagents required to do the three reductions, the alkyne can be reduced all the way to the alkane by simply using hydrogen and a metal catalyst. And so that's the first reaction here. And you see pentyne is going all the way to pentane. Do notice next to the H2 I have excess written in parentheses. And palladium over carbon is just a typical catalyst for doing a reduction. You saw the same catalyst used in the case of alkenes. Example number 2 uses hydrogen and something referred to as Lindlar catalyst. Now, Lindlar catalyst is a variation on the regular metal catalyst. What has been done to the metal catalyst is what is referred to as poisoning. That means that the metal catalyst is a little less reactive Since alkynes are more reactive than alkenes to start with, if you're using a catalyst that's a little less reactive, it's only able to add one equivalent of hydrogen across the triple bond and thereby take a triple bond to a double bond and leave it there. Lindlar catalysts will produce the cis alkene. And the reason for that is, if you remember the chemistry of the metal catalyst in the case of hydrogenation, the hydrogens are always added in a syn addition. That is, both hydrogens must come in from the same side. So they add across one particular pi bond from the same side. That's why the cis alkene is produced. The third set of conditions is quite different. That, if you notice on the arrow, is sodium metal. Remember the superscript 0 always indicates that we are using the metal, not an ion. And so sodium metal is dissolved in liquid ammonia, and that liberates electrons, at least theoretically, according to the mechanism that's most likely involved in this reaction. And so in this particular case, what's really happening is electrons are being added to the alkyne to produce an anion. The anion gets protonated by the ammonia, and then another electron gets added to generate another anion, and a second protonation occurs from the ammonia to the intermediate. Now, because this is electron chemistry and not a metal catalyst, the two hydrogens that are added are not added in a concerted fashion and do not have to go in from the same side. That is, it does not have to be a syn addition. Bonds are free to rotate during the process, and because of that, the thermodynamically more stable trans alkene is generated as the product. Okay, and so there you see the three reactions that you need to know about for reduction of alkynes, all the way to the alkane using excess hydrogen and a metal catalyst, using hydrogen and a poison catalyst, typically Lindlar catalyst, to give the cis alkene, and using dissolving metal reduction to give the trans alkene. That's it for the actual chemistry of the carbon-carbon triple bond, but there's some chemistry that can be done on the proton that's attached to an sp hybrid carbon, as you see in terminal alkynes. And that particular proton turns out to be extra acidic relative to other hydrogens that are attached to carbons in other hydrocarbons. So the sp hybrid carbon presents a special case in that hydrogens attached to it are sufficiently acidic to be useful in reactions. And on this particular slide, you notice that you see an sp3 hybrid carbon, sp2, and sp hybrid carbons to show the difference. Now, when a proton is removed from the carbon, of course, you get a carbanion, and the carbanion right there has a negative charge on it. And we really haven't had a chance to talk about carbanion chemistry yet. Carbanion chemistry tends to be a topic of organic 2, whereas organic 1, the tendency is to stick with carbocations. Let's see. When you think about the pKa values, and that's the indication as to how acidic a particular compound might be. If you look at an ordinary alkane, ordinary alkanes have a pKa of about 55 to 60, somewhere in that range. Alkenes have a pKa that's about 42. Whoops, I guess I went too far with that. Well, anyway, and alkynes have a pKa of about 25. Now think about that, a pKa of 25. That is in a range that's beginning to be much more useful chemically speaking. One way to generate a carbanion from an alkyne is by reaction with a base that's sufficiently strong to remove that proton. And the base that works the best is sodium amide. And you see that at the bottom of this slide. Sodium amide has a nitrogen with a negative charge. Now ammonia, as it states right above that, ammonia has a pKa of about 35. So that means ammonia is less acidic than a terminal alkyne, and that means that the conjugate base of ammonia would be protonated by a terminal alkyne, and that's why the reaction works. And you see that at the bottom here. The reaction of the amide, that's the name of the conjugate base of ammonia, amide successfully removes the proton from a terminal alkyne, leading to a carbanion. And that's just simply because of the relative pKa's and therefore the equilibrium of the acid-base reaction. Once we do that, we can use the carbanion to do some other chemistry. Now, one common procedure is to make a Grignard reagent from terminal alkynes through this method. Can't make a Grignard reagent from a terminal alkyne that would have a bromine on it the way you did with bromobenzene in lab. Instead, what we do is take a terminal alkyne, react it with, Instead, what we do is take a terminal alkyne and react it with a Grignard reagent. That, too, is an acid-base reaction, and since the pKa of ethane is about 55 or so, and the pKa of the terminal alkyne is 25, the reaction moves forward quite readily to generate an acetylenic Grignard reagent. And then we can use that further. As it says here, the 1-haloalkynes are not generally available commercially, so you can't make a Grignard as you did in lab, I should say. And then once the Grignard is made, you could use it in some other reaction, which we'll look at later on. When you try to think about the pKa value of a terminal alkyne, there are actually two factors involved. One of those is bond strength, right? There's bond strength involved, and there's also electronegativity involved. Electronegativity helps to stabilize the anion that's generated, but bond strength talks about how strong the hydrogen is held to the carbon. And notice that the terminal alkynes have a very strong bond relative to alkanes or even alkenes. 130 kcals per mole compared to just 100 kcals per mole for the alkanes. The stronger the bond, of course, the harder it is to break. And so when you think about those two factors, then the electronegativity is helping to stabilize the anion that's formed, but the strength of the bond is trying to keep the compound protonated. So between the two, we understand that the electronegativity of the carbon must be sufficiently strong to overcome the bond strength and lead to the acidity that is seen for terminal alkynes. And so the electronegativity is the more important factor, and we see that right there. It must outweigh the effects of bond strength. Electronegativity increases through the hybridization, and that's a trend that's seen throughout the atoms that we consider to be hybridized. We see that acidity increases with hybridization change from sp3 to sp2 to sp. And one rationalization for why hybridization matters is that with increasing S character, the electrons are more stable, and thus consider the atom to be more electronegative in the sp hybrid state from the sp3 hybrid state. One way to think about S character, and that's an interesting concept in and of itself, is just what is S character. But if you think about sp3 hybridization as being 1 part S and 3 part P, then it's 25% S. And sp2 would then be 1 part S and 2 part P, therefore 33% S. sp, of course, is 50% S. And so it has the most S character and thereby the most stable for electrons. And here's a reaction showing the use of a terminal alkyne, in this case actually acetylene itself, in a reaction with an electrophile to build a bond. And so you see sodium acetylide, the anion of acetylene reacting with 1-bromobutane to give a new compound, 1-hexyne. And so we see a new carbon-carbon bond is built between the nucleophilic carbon and the electrophilic carbon. And then because 1-hexyne is also a terminal alkyne, you see it being used then in a second reaction where it is just simply being methylated with methylbromine and to yield a new compound, which would be 2-heptyne. Okay. And that's pretty much it. This ending slide just shows a pheromone trap. We got this out of a different book. The pheromone in particular that's being used is an alkyne. It's kind of a nasty trick to do to this particular moth, but it's an effective trick. And that's it, I believe. Enjoy your break.